now that we have seen torque, let's do a few examples and see how this actually works. So, first example, so let's say that we have a rotating door which is pivoted at its center. So I'm going to draw from the top view, but here's my rotating door. This thing is pivoted at the center point here. So this is our pivot point. So let's say that we have two businessmen who are trying to get into the building, and each one wants to get there first so they can actually sell their product. So let's say that we have our two businessmen. So the first one then is going to apply a torque, or at least a force. Let's call this guy over here. He applies a force F1, which is then equal to 625 newtons, and he's going to be at a distance of 1.2 meters away from the pivot point. So the second businessman, he says, well, I've looked at physics before. I know all these things. So I'm going to go a little bit shorter and apply a little bit bigger force. And now we want to know. So he's going to apply a force F2, which is 850 newtons. But he's going to do it only at a distance of 0.8 meters away. So what we want to know then is which one of these two guys is actually going to win. So which one is actually going to get into the building first, so he can sell his products first. Which basically means we want to simply look at the net torque. So we want to know, again, which one wins. So we want to know which one is applying a greater amount of torque. So let's just simply look at the net torque on it. Now, first of all, let's think about the torque from each one of these guys. Now, what's happening is the first guy is applying a force here, this distance away, so he wants to rotate the door in this direction. So if I push my force here, here's my pivot point, apply the force in this direction, he's going to rotate it this way. This is then a clockwise rotation, so he's applying a negative torque. Simultaneously, this guy's applying a force here, going to rotate in this direction, so this is going to rotate in a counterclockwise direction, so this would be then a positive torque. So in this case, what we know is that this one is going to be a negative torque, this one is going to be a positive torque, which means that the net torque is simply going to be the difference between these two torques. So the question of who is going to win is equivalent to what's the sign on the net torque? Is the net torque positive or negative? If it is positive, what that means is it's going to rotate this way, so this guy is going to win. If it's a negative, it means that overall the door is going to rotate this way, so this guy is going to win. So good. Now, the net torque then is simply equal to the sum of all possible torques. So this is then going to be equal to the torque by 1 plus the torque then by 2. Now, what we know is that this is equal to then what? Since this is a negative torque, so it's going to be negative R1 times F1 times sine of the angle between them, so let's call that theta 1, plus R2 times F2 times sine of the angle between those two. So in this case, the vector R1 is the vector which points from the pivot point to the location of the force, so that's this guy. The force is in this direction, which means that these two are actually at a 90-degree angle to each other, so theta 1 is simply equal to 90 degrees. And sine of 90 we know is simply equal to 1. Theta 2, again, R2 is going to be the vector which points from the pivot point to where the force is acting. So in this case, this is going to be R2. F2 goes off in this direction. So again, these two are at a 90-degree angle from each other. So theta 2 is also simply equal to 90 degrees, which means in both of these cases, sine of 90 is simply equal to 1. So this is the same thing then as minus R1 times F1 plus R2 times F2. Plug in my numbers, what I find in this case then is that the net torque is equal to minus 70 newtons times meters. So in this case, salesman 1 wins. Now, other thing to point out here is if we go back to work, remember work was force times distance times cosine angle between the two. Torque is force times distance times sine angle between the two, which means that if we thought about dimensional analysis, torque has units of force times meters, which is the same thing as a newton times a meter. Now, when it came to work, what we said was work had units of newton times meters, which is what we call a joule. Now, when it comes to torque, that's not true anymore. So even though it has exactly the same units as energy, meaning a newton times a meter, but again, an energy is a scalar quantity, which means that there's no directional properties associated with it all. So that has a joule because that is a scalar quantity. Unlike torque, which is now a vectorial quantity, which means direction does matter. So even though the units are the same, we're talking about two physically different quantities, which means that these two have different units to them. So when it comes to energy, the units are joules. When it comes to torque, the units are Newton meters. We don't call that a joule. So just keep that in mind. So let's do another example. So next example says that we're going to have a wheel or a pulley. So here's my pulley. And this thing has a radius of r. We're going to apply a force to this thing perpendicular to the pulley itself. And the pulley has a moment of inertia, which is equal to 1 times 10 to the minus third kilograms meters squared. And this thing has a radius of 10 centimeters. So the radius of this thing is 10 centimeters. And here we're going to apply a force, which is actually a time-dependent force. So this goes at 0.5 times time plus 0.3 times time squared, where this thing has overall units of newtons. Okay, so this is a time-dependent force. So what I want to know in this case then is, put a 90 degree on there, at time is equal to 3 seconds, part A, what is the angular acceleration? So what is the angular acceleration that this wheel is feeling? And then part B, what I want to know is what is the angular velocity at 3 seconds? So this thing starts off with, at t is equal to 0, 0 force, and we're going to assume that the initial angular velocity is equal to 0. This thing then is going to feel an angular acceleration in the direction of the torque, or the direction of the force in this case, which means it's going to rotate this way. So at the end of 3 seconds, this thing is going to have an angular velocity rotating this way. So we want to know what is that angular velocity at the end of 3 seconds. So good. So let's look at part A first. So part A says we want to know what is the angular acceleration. So to get the angular acceleration, we're going to look at simply the analog of Newton's second law, where it says that the sum of the torques acting on the system is equal to the moment of inertia times the angular acceleration. Now, in this case, there is only one torque acting on it, and that's simply from this force. So we're going to say that this is equal to r times the force times sine angle between the two is equal to the moment of inertia times the angular acceleration. Which tells me then that based off of Newton's second law, the angular acceleration is going to be r times f times sine angle between the two times the moment of inertia. Now, in this case, r is the vector which points, again, from the pivot point to where the force is acting. So this is my r vector. Force is off in this direction, which is acting tangentially to the circle, which means by definition, these two are at a 90-degree angle. Sine of 90 is simply equal to 1, so it's going to be the same thing then as r times f divided by the moment of inertia is equal to the angular acceleration. So let's plug in what we know. So this is going to be r, which is 10 centimeters, which is 0.1 meters, times the force at 3 seconds. So it's going to be 0.5 times 3 plus 0.3 times 3 squared, all divided by the moment of inertia, which is 1 times 10 to the minus 3, and that's equal to the angular acceleration. So finish multiplying this out. What I get in this case then is that the angular acceleration is about 420 radians per second squared is equal to the angular acceleration. Now, to get the angular velocity, remember that, by definition, for part B, angular acceleration is equal to the time rate of change of the angular velocity. So this means that since the angular acceleration is time dependent, to find the velocity at a given point, we can't simply find what the initial velocity was and then find what the final velocity is and then simply plug it in that way, but we're going to have to do an integral over the angular acceleration. So let's do that. So we want to integrate to find the final angular velocity. So from here, multiplying both sides by dt and then doing an integral. So on the left-hand side, I'm going to have the integral of d omega integrated from the initial angular velocity to the final. is equal to the integral of the angular acceleration integrated over time from the initial time to the final time of t final. So left-hand side is just going to be the final angular velocity minus the initial angular velocity is then equal to, so let's put in our values here. Now r and I are both constants, so we can pull those out of the integral. So this is going to become r divided by I, integral of the force integrated over time from the initial time, which is 0, to the final time. So use our values. So this is then going to be equal to r divided by the moment of inertia times the integral then of 0.5 times t plus 0.3 times t squared integrated over dt from 0 to t. Again, I'm going to write this as two separate integrals. So if I integrate this one, this is going to be 0.5 times t squared divided by 2, so that's 0.25. Times 0.25 times t squared plus, so here, 0.3 stays constant, so it's going to be t cubed divided by 3, so it's going to be 0.1 times t cubed, all evaluated from 0 to, in this case, 3 seconds. Plug in our values, what we find in this case then is that the final angular velocity is 500 radians per second. This is our final angular velocity. Good. So one more example. Or actually, no, sorry, two more examples. So the next example is going to look at the last example we did in the previous, which is we're going to look at an object rolling down an inclined plane, and we want to know is what is the velocity by the time it reaches the bottom. So again, I want to look at this scenario. So here's my inclined plane. This is at an angle of theta. Put some object here. This thing is going to roll without slipping until it gets to the bottom. And again, what I want to know is what is the center of mass velocity by the time this reaches the bottom. But this time, instead of using conservation of energy, we're going to use now our new friend, which is torque. Okay? So we want to use this to find torque, which essentially means that we want to know what is the center of mass acceleration of this guy as he slides down, and then use that center of mass acceleration, using the fact that we know it's going to move this total distance of L, based off of this height change, h here, to then find that velocity. Now, we already know the answer. We already found this using conservation of energy. Let's remind ourselves what the final velocity was. We found that the center mass velocity was equal to the square root of 2 times g times h divided by 1 plus c, where c was the moment of inertia of the object. So our answer that we get here using torque better match this exact answer that we get here. So let's do this. So first thing we want to do is draw a free body diagram. So here is my object, which is going to roll down. So what forces do I have acting on my object? Well, we know this object is not falling through the plane, which means there has to be a normal force. So that normal force then is going to point off in this direction. We know there's a center of mass weight to it, so there has to be a gravitational force. So we have mg acting in this direction. Now, technically, I drew this a little bit wrong because the normal force is not actually acting at the center of mass. It actually acts between where the mass is attached to the plane, which means it's actually acting at this location. And finally, what's causing it to rotate, again, is the static friction. Now, again, this object is going to roll in this direction, which actually means the static friction will be acting this way, which causes it to actually roll in this direction. And we know that this thing is going to have a center of mass acceleration. That center of mass acceleration is going to be down the plane. Good. Now, first things first, let's look at the sum of the forces. So in this case, we can break this thing up then into the y direction. So let me call this the y direction. Let me call this then the x direction. Now let's look at the sum of the forces in the x direction. So we can So the sum of the forces in the x direction is equal to the mass of the object. So let's say this mass has a mass of little m, times then the center of mass acceleration. So in this case, what is acting down the plane then is this portion of mg, where this is the same angle as the plane. So this is going to be mg sine of theta, minus then the static friction force, which is then acting up the plane. Now, as we said a long time ago, when it comes to static friction is anywhere between its minimum value, which is 0, up to some maximum value, which is mu sub s times the normal force. Now, if all we knew was Newton's second law for linear forces, we couldn't go any further with this without assuming that this thing had maximum static friction, which means we'd have to look at some of the forces in the y direction and get that the normal force is simply equal to mg cosine of theta. But as this object is rolling down the plane, there's no reason to believe that it's maximum static friction acting on this thing the entire time. So to say that would actually be wrong. It would be false. So what we need to do then is what? Consider the torque, because this thing is actually going to be rotating as well. So simultaneously, we need to be looking at the sum of the torques. So in this case, we want to look at the sum of the torques, whereby the analog of Newton's second law says this is equal to the sum of the moment of inertia times the angular acceleration. Now, just like the velocity, what's true about the angular acceleration is that's not independent of this center of mass acceleration. These two are actually related to each other by the radius of the object. So if this thing has a radius of, say, little r, these two are related this way. So I can actually rewrite this then as the moment of inertia times then the center of mass acceleration divided by r. Now in this case, what I want to do is I'm going to take the sum of the torques about the center of mass. And the reason for that is basically I want to rewrite this static friction because I don't know what the static friction is, but I can use the torque to determine exactly what that static friction is. So let's do it about the center of mass. So in this case, I'm going to take the sum of the torques about the center of mass, which means this is the moment of inertia about the center of mass, is I'm going to be multiplied by the linear acceleration of the center of mass divided by the radius. Good. So now let's look at the torques. So this says that the net torque is about the center of mass. So what is actually causing a net torque? So let's first look at the normal force. So for the normal force, we have normal force is pointing in this direction. The r vector is the vector which points from the center of mass to where that force is acting, which in this case would be in this direction, which means that my r vector is pointing down this way. My normal force is pointing this way, but the angle between these two is 180 degrees, and sine of 180 degrees is equal to 0. So what this says then is that there is no torque generated by the normal force. Great. So now let's look at the gravitational force. So the gravitational force, so in this case, the r vector is going to be the vector which points from the pivot point to where the force is acting, but notice that the force is acting directly at the pivot point, which means the distance between the two is simply 0. So when I write out my torque, which is the distance times the force times the angle between the two, but the distance is 0, which means that the torque generated by the gravitational force is also 0. Which means that the only thing which is generating a torque is actually the static friction. So the only thing which is generating this is the torque from the static friction. Now in this case, the r vector is the same as the green one here, points from the pivot point to where the force is acting. The force is acting tangentially to the circle, which means the angle between the two is 90 degrees. So this is now just going to be r times the static friction is equal to the moment of inertia about the center of mass times the center of mass acceleration, all divided by the radius. So from here, I can finally say that the static friction is then equal to the moment of inertia divided by the radius squared, all times the center of mass acceleration. Good. So now we can take that and plug that in here. So this becomes then m times g times sine of the angle minus then the moment of inertia about the center of mass times the center of mass acceleration, all divided by the radius squared. Is then equal to the mass times the center of mass acceleration. Now, since I have a center of mass acceleration here and here, I'm going to bring this guy over here, factor out, and then divide. So finally what I'm going to get is that the center of mass acceleration is equal to mg times sine of theta, all divided by the mass plus the center of mass moment of inertia divided by the radius squared. Good, so this gives me then the center of mass acceleration. So now that I know the center of mass acceleration, we can go back to what we did in chapter 2, which is look at linear kinematic equations, given the fact that we know this thing travels a distance of L down the plane, to then find the velocity by the time it reaches the bottom. So using kinematic equation number 3, that says that the final velocity squared, which will be the final center of mass velocity, is equal to the initial velocity squared plus twice the acceleration, which in this case is the center of mass acceleration, times that distance it travels, which is simply L. Now the initial velocity was equal to 0, which means the center of mass velocity then is equal to the square root of 2 times m times g times L times sine of the angle, all divided by the mass, plus the moment of inertia about the center of mass divided by r squared. Now, as we talked about before, certain things we know. We know that the center of mass moment of inertia is always going to be equal to some constant times the mass of the object times the radius squared, which means the r squareds are going to cancel. This m is the same as this m, which is the same as this m. Those m's are all going to cancel. And finally, we know that h here, since this is the opposite side related to that triangle, h is going to be the same thing as L sine theta. So that L sine theta is the same thing as h. So finally, writing everything out, we get that this is equal to the square root of 2gh divided by 1 plus c. These two things are exactly the same as they should be. So we indeed get exactly the same answer as we should. If we didn't, something would be wrong. So that would not be a good idea. Good. So our last example, we're going to go back to the Atwood machine. So let's look at the Atwood machine, and let's do the Atwood machine. Again, not using conservation of energy, but looking at torque. So this one says we have an Atwood machine which has 2 masses hanging from it. So here's my Atwood machine. I have a mass on this side, call that M1. Mass on this side, call this guy M2. And the Atwood machine itself has its own mass, M, and has a radius of capital R. So let's give some numbers here. So M1 is equal to, oops, sorry, let's do that backwards. So let's call this one M2 down here, M1 up here. So M1 is 10 kilograms, M2 is equal to 5 kilograms, M is equal to 6 kilograms, and the radius is equal to 0.5 meters. So in this case, what I want to know is, what is the acceleration of the system? So what is that acceleration of the system? So good. Now, since this is now a massive pulley which is rotating, this thing is going to have a tangential acceleration based off of that angular acceleration. This is going to have a linear acceleration since it's going to accelerate upward. This one's going to have a linear acceleration downward. But again, this one is communicated to this one by the fact that this tension here is related to this tension. But here we have to be careful because when this thing was massless and frictionless, these two tensions were the same. But that's not the case anymore. And this is not the case because this thing is rotating. So again, if this thing is going to rotate in this direction, what has to be true then is that how hard I'm pulling on this side must be greater than how hard I'm pulling on this side to get this thing to rotate in this way. So what that means is that this side over here has to have a greater tension than what's going on over here. So I have to label them as 2 different tensions. Now, but if I look at the pulley itself, the pulley is going to have those 2 tensions, which is going to relate to the fact that this thing also has a tangential acceleration. So what this means then is I'm going to have to draw 3 different free body diagrams, one for M1, one for M2, one for the pulley. But since this one is moving linearly and this one's moving linearly, I'm only going to consider Newton's second law. And for this one, I'm going to consider the analog of Newton's second law. So let's draw free body diagrams. So let's do one for M1, let's do one for M2, and let's do one for the pulley. So good. So what forces are acting on M1? Well, we know M1 has gravity, so we have an M1G down in this direction. Also has a tension, and let's call that one simply tension T1 going upward. M2, that also has gravity, so there must be an M2G this way, has its own tension, so this is going to be a tension T2. But the difference between these is that they're accelerating in opposite directions. Right? This one's going to accelerate this way, and this one is going to accelerate this way. Finally, let's look at the pulley. So the pulley is being pulled down in this direction by T2, being pulled, T1, pulled down in this direction by T2. Now this thing does have a center of mass gravity to it, and it also has a normal force because this thing is going to be held up in some manner. Now as far as the angular acceleration is concerned, those two things don't matter. Neither one of them are going to cause a torque, and I know that because this thing is going to be rotating about its center of mass, and the gravitational and the normal force are going to be acting along this line, which means they give no torque to them. Now, that normal force would become important if I was saying, for example, what material do I need to construct this thing so it didn't fall down and break? In that case, I would need to know the normal force, and that normal force would be dependent both on the gravitational weight as well as those two tensions. But in this case, all I care about is that acceleration, so that's not an important quantity to me. But what I do know is that this thing is going to rotate in this direction, which means that the only thing I care about is Newton's second law, the angular version of that guy. So good. So let's apply Newton's second law. So for the M1, we're going to take that. Positive y direction is this way. M2, we're going to take positive y direction is this way. Remember, we always want a y direction to go in the direction of the actual acceleration. This guy's going to rotate this way. So even though this is technically a negative torque overall, but again, since Newton's second law is a vectorial statement, that means I would have to take into effect that the angular acceleration will also be negative. Now, in this case, I'm going to pretend that this way is actually positive. Doesn't change anything, just means I'm multiplying through by a negative sign. That way I just don't have to worry about that negative at the end of the day. So it means I'm not going to call this guy a positive torque, this one a negative torque. I'm actually going to call this one positive, this one negative, taking into effect that the angular acceleration has a negative sign. So good, so let's look at mass 1. So for M1, we can say the sum of the forces in the y direction are equal to Ma. So in this case, I'm going to get what? An M1G minus T1 is equal to M1A. For M2, we then get sum of the forces in the y direction are equal to M2A. So here I get T2 minus M2A is equal to M2A. So T2 minus M2G is equal to M2A. For the pulley, we then get that the sum of the torques. So for the pulley, we get that the sum of the torques are equal to the angular moment of inertia about the center of mass times then that angular acceleration. Now, again, what has to be true is that what? This guy has an acceleration downward. This point here also has to have exactly the same tangential acceleration, which is exactly the same as the linear acceleration of M1. This point here, M2 is accelerating upward, but this point here has to have exactly the same tangential acceleration as M2, and we know that M2 has to have the same linear acceleration as M1, since our chord is not elongating or stretching or doing anything like that, which means that they all have to have exactly the same acceleration. And again, what we know is that the acceleration at this point is not independent of the angular acceleration, it's actually dependent on the angular acceleration by the radius of this object, where the radius of this object is capital R. So here I'm going to replace this guy with simply that same acceleration divided by the radius. Now, again, this thing is feeling a positive torque from this guy. Again, even though it's negative, we're going to call it positive for now. Feeling a negative torque from this guy. So I'm going to rewrite this then as what? R times T1 minus T2, where in this case, R, again, is the vector which points from the pivot point to the location of the force, which means that this is a 90 degree. R, in this case, we point in this direction, which again means it's 90 degrees. So again, sine of 90 is equal to 1. So good. So here I get a T1 minus a T2. Here I have a T2. Here I have a T1. So all I have to do then is what? Solve this guy for T1, plug that in here. Solve this guy for T2, plug it in here. And then that'll finally give me an and acceleration and acceleration and acceleration. And then we can put all those things together to find the total acceleration. So let's do that. So good. So first things first, notice here I have a negative t1, here I have a positive t2, so I'm going to simply add those two things together. And that's going to give me this up to a negative sign. So let's do that. So this is going to give me an m1g minus m2g. And then I get a plus t2 minus t1 is equal to m1 plus m2 all times a. Good. Now what I want is actually t1 minus t2, so I'm going to bring these to this side and this to this side. So this is going to give me an m1 minus m2 times g minus m1 plus m2 times a is equal to t1 minus t2. Now that I have that, I'm going to simply put that in here, divide both sides by the radius, and then finally solve for the acceleration. So let's do that. So this is going to give me a moment of inertia about the center of mass times the acceleration, all divided by r squared, is then equal to t1 minus t2, which is equal to this. So it's going to be m1 minus an m2 times g minus m1 plus m2 times a. But notice here I have an a, here I also have an a, so I have to bring this term to this side, factor out the a, and then eventually solve for a. So I do that, I get a then is equal to m1 minus m2 divided by m1 plus m2 plus moment of inertia about the center of mass divided by the radius squared, all times the acceleration due to gravity. Now, let's do a quick dimensional analysis. Again, we know this is some constant times the mass divided by the radius squared, so the radius squared is going to cancel. So this is then mass divided by mass, which is dimensionless, times an acceleration, so I get acceleration is equal to acceleration. So dimensionally wise, this thing is correct. Now, if I assume the fact that the pulley, in this case, is a solid disk, what I know in this case then is the moment of inertia about the center of mass is equal to 1/2 times the mass times the radius squared. So this is going to become 1/2 the mass. Look at my numbers. What I get in this case then is that the final acceleration is 3.27 meters per second squared. So this is my acceleration of this system. Now, again, if I compare this acceleration to the acceleration I would have without the rotation of the pulley, this is going to have a lower acceleration. This has a lower acceleration for exactly the same reason as before. It takes work for me to rotate this thing, which means it takes more force for me to rotate it, which means if it takes more force, i.e. torque in this case, then the force which is pulling down has to be diverted, which means I have to put more force into causing that thing to rotate, which means the acceleration can't be as great.